So, welcome everyone to Guided Study Group Week 11 of my 141 this semester. So, which is this week is, as you know, this week it's the exam week, so we wouldn't have any new materials. And so we're just gonna be doing exam review this time. And luckily, a lot of you already did the practice exam, so I think it's a very good sign. And so I will just base some of my questions on there and see how like based on the need of the people, because I saw some of the questions you guys got it wrong. Maybe it's been like a while since you've been touching on that topic or so on. So I've chosen some of those questions in the practice exam where you can work on that, but I didn't actually specify so that you guys wouldn't just use the answer for these questions into your practice exam. Now, having said that, let's get started. So, first piece of materials for exam 2 is indeterminate forms of limit and L'Hopital rule. So you have 7 indeterminate form, which is 0 over 0, infinity over infinity, infinity minus infinity, and the free product, the product form, which is infinity multiplied 0, and free of a power form, 1 to the infinity, 0 to 0, or infinity to 0. Now, note that 0, so not 0 to the infinity or infinity to infinity. So very important there. So there are 2 ways. If it's already there are 4 ways. If it already put in the quotient, you're gonna use the L'Hopital rule just by taking derivative of the numerator and denominator separately. Product, if it's given in the product, you have to make it into the quotient first using this expression, this kind of like transformation of algebra. And then if it has the difference, again, our entire point just trying to make it into a quotient using common denominator conjugations or even this property of log, and then you start use the L'Hopital rule. And then finally, if you have a power, first you have to make it into a product, then a quotient, using again this expression. And we're going to see that's very clearly in one of our example. Then we have improper integrals. So this is kind of like not a very hard part of the materials, but somehow when I look at the questions that you guys already did for the practice exam, and I saw a lot of people got it wrong somehow. So I kind of put like 1 or 2 questions in the practice exercise trying to get you guys remember and see like maybe if you have got that one wrong, you can track back on which step of the problem that you got it wrong. So there are 2 types of improper integrals. It's infinite integral or discontinuity integral. So infinite integral is when you have a discontinuity in the domain that you look for integral. So say you integrate on an interval, but there was one point in that interval that your expression is not continuous. Or you can have like infinite integral is when you have one of the boundaries related to infinity or negative infinity. And discontinuity integral is the one that I just said. Sorry, I kind of like mixed them up. But I mean, essentially, you guys understand what I'm saying. So it's like type 1 is the one that have infinity or negative infinity in one of the boundaries, or both. And type 2 is when you have one of the discontinuity either at the endpoints of the interval that you're taking integration on, or at one point in the middle of that interval. And if it's in the middle, you have to put it into, you have to find the 2 individual integral first, kind of like split that interval into, say, from A to B, and then you have C in between. You have to find the integral from A to C and C to B first. And then if both of them are convergent, then you can say that the initial integral is equal to their sum. Then you have sequence. So sequence is kind of like just a list of a lot of numbers that it can have a roots with one another, it might not. Then you have that sequence is convergent. If you have limit of n approaching infinity of the nth term of a sequence exists, now note that sequence is very different from series, that such that if the limit just need to exist and no matter what value it is just need to be a number, then the sequence is convergent, while the series might not be convergent if that limit is different from 0. So then you have that one is convergence sequence. You have monotonic, which is just either increasing or decreasing sequence. We have bounded sequence, is bounded above or bounded below. And if it's both bounded and monotonic, then it's convergent. And you also have the squeeze theorem for sequence, where if you can squeeze a sequence, the nth term of a sequence in between two sequence, then if the limit of those two sequence are both L, then the thing in between the squeeze sequence is also having the same limit at ends approaching infinity. This is kind of like mostly theory. Then we jump to series and start to use a lot of tests to identify what is if the series is convergent, divergent, or even absolutely convergent or conditionally convergent. Now all of the tests I already put it here. You guys can have a look later when you start to review this slide and maybe review these sessions. So you have test of divergent, integral test, alternating test, direct comparison test, limit comparison test, ratio, and root test, where you can I have some of the warnings over there as well. So kind of like read through all of them and make sure that you understand all the point I put there. I kind of like summarize everything. I think I add something as well. But if you have any problems trying to understand this slide or this table later, even just the detail in here, make sure that you email me and I'll try to clarify the most out of you for you. So now we're gonna go to do some of the example questions. So the first one is evaluate this one. So clearly it looks like a very normal integration, except for the fact that you have a discontinuity in the denominator at discontinuity in the denominator at x equal -1. Therefore here it's in between, so I'm gonna identify the two complementary integral to find what is if both of them are convergent, then you can conclude that the total integral is also convergent. So you have limit of t approaching negative minus -2 to t 1 to the x plus 1 dx. This one is limit t approaching minus ln x plus 1. And you have from -1 or from t to -2. And this one is just so clearly here, when you start plugging in -1, so if I just put this ln of t plus 1 minus ln of 3 or ln of 1. -2 plus 1 is just -1, but you take the absolute value, so it's just going to be ln of 1, which is 0. So here, if you look at this, as t approaching -1 minus, ln of t plus 1 is going to approach ln of with the absolute value, so it's going to approach ln of 0 plus, which is going to give us negative infinity, because this one is going to be 0 plus. because you have also the absolute value, so it has to be positive. So this entire ln approaching negative infinity. So from here, you don't even need to do the second one, and you can immediately conclude that this integral is divergent. Yeah, I mean, this one is mostly just plugging in, or maybe I think some of the questions, some of the people can get it wrong in this last step, or you can get it wrong maybe just like in the taking integral. So if you forgot the absolute value side, it can change the entire thing. Now that's first questions. The second one, I also found that at least 2 or 3 people got it wrong, which is again kind of weird to me, but we can try working on that. Again, you have a discontinuous in the denominator at -1 again, so you're gonna have L limit t approaching 0, 1 plus, because now it's only on the right from t to 1, 1 over square root of x. Or I can rewrite it in this way, x plus 1 to the negative half dx. Now, if you want to take the integral of this, you're going to have, say, 2 x plus 1 to the half. And then you go from 1 to t. Then this one is limit t approaching -1 plus 2 x plus 1 to the half. So here is just going to be the first number is going to be when you plug in 1 in. So it's going to be 2 square root of 2 minus limit t approaching -1 plus 2t plus 1 to the half. And so clearly, when you plug in t equal to -1 to the right here, then it's going to give you something. This thing inside is going to be 0 plus. So what it's giving you is going to be just 2 square root of 2, because limit 2 times 0 to the half, so square root of 0 plus, it's just going to the entire thing as t approaching -1 plus. This thing is going closer to 0. So this thing, entire thing is just 0. So you keep that 2 square root of 2. And so this is our answer is convergent, and it's the integral converges, and it converges to 2 square root of 2. Again, this is a very simple one, and I couldn't really understand why. 'Cause it seems like a lot of 2 or 3, at least 2 or 3 of the students actually make this mistake. So I just maybe the problem lies in where you plug the value in or where you find the integration. So if that's the reason, just make sure that you check your calculations in the exam. Then we have that. The next one is indeterminate form, but we don't know what form is it. Just so the first thing always gonna do is plug in. So when you plug in 0, you're gonna have 1 plus 0, so 1 to the infinity. So this is where you're gonna use put it into a product first and then a quotient. So you have this limit of x approaching 0, e to the 2x plus x to the 1 over x. This one is equal to e limit of x approaching 0, 1 over x multiply ln of e to the 2x plus x. Now we're going to find just that limit. It's going to be so now here, if you plug in 0, what you have is 0 over 0. So I'm going to take the L'Hopital rule of this. You're going to have ln, oh no, when you take derivative, you're going to have 2 e to the 2x plus 1 divided by e to the 2x plus x. Give me a second. Divided by just 1, which is if you put it in algebra, kind of like simplify the denominator. E to the 2x plus 1 divided by e to the 2x plus x. Now you have to plug in first to see if it's still in the indeterminate form if you want to continue taking L'Hopital rule. So when you plug in x equals 0, you're going to have it's equal to 2. Right? No, actually you're going to have 3 divided by 1, so it's going to be 3. So this limit approaching 3, and so you plug it back in, is going to be e to e cubed. So nothing new, just try to remember the technique of what you have to do, and as long as you understand the technique and the reason behind it, you should be able to solve all the problems. So that's the third questions. The next one I have is to write this one as a fraction. So as I said, as I did one of this example before in I think week 8 or something. So the way we're gonna do, week 6. So the way we're gonna do it is, you have 1.333. So I'm just gonna write at this this notation. So it's gonna be 1 plus 0.3 plus 0.03 plus 0.003 until infinity. And this one is going to give you 1 plus. So I'll write it in the form of fraction and you see the chains. As you can see here, except for the first term of 1, every ensuing term, we're gonna be 1/10 away from one another. So it's going to be 1 plus the series from 1 to infinity, or maybe 0 to infinity, 3/5, 3/10, and then the next one is 1/10. Now to determine if it's to the n or to the n minus 1, just plug in n equals 0 for this. So if you started at n equals 0, and the first term of ours is 3/10, so you want 1/10 to the n is going to be equal 1. So n here is going to be 0. So the power here is 0. So it have to be to the n. However, if you started at 1, it's going to be the series 3/10 multiply 1/10. But now, the first term you just want it to be 3/10. So this thing over here is to the 0. And so yeah, it's going to be n minus 1. Because n minus 1 here, when n equal to 1 is 0. So it's just depending on how you define your system. And then you're going to have a different starting point and different power. But in the end of the day, it's just going to equal to one of the sum. But the sum here is going to be, it's again, when you're trying to use this formula, a to r n minus 1, or whatever thing is, as long as it's the geometric series, is a 1 minus r. With a always is the first term in that sequence. First term is basically you plug in the first value of n into the series. So you have that is going 3/10, 1 minus 1/10, with r is equal 1/10. This one is just going to be 1 plus 3/9, which is 4/3. So this is my final answer for this questions. So again, this is a consequence, a convergent series, based on geometric series where you have the multiplying factor be equal 1/10, smaller than 1, so it's convergent. And you just use that formula to find the sum, by using a is the first term in the series and r is just a factor. So again, this is not new, just trying to like retrieve it for you guys because it's been a while since we touched on these materials. Now the next one, which integrals below converges. I think this is one of the questions that most of the people got wrong. As I checked through, it's not a lot of you guys already did the practice exam, like 5 people. At least 3 or 4 of them get this one wrong. So I think this one is a very helpful. It has three parts, and then just like choosing one of the series that is converges. So I think this one, this questions, most of the people got it, but the next one is kind of like a challenging one somehow. So to find this one, again, we're going to use limit t approaching infinity of 0 to t 3x squared e to the negative x cubed dx. This one, if we use a simple substitution, you're gonna have limit of t approaching infinity. If you put u as x cubed, so it's going to be 0 to t e to a negative u du. You have du is 3x squared dx. Note that the boundary here doesn't really change because when you have x and u going from 0 to infinity, this one is also the same. So not really a change in the boundaries. Now after that, you have negative e to negative u when you take integral of that. So it's going to be from 0 to t. And so this one is oh yeah, you have that limit. I forgot. Limit of t approaching infinity. So you have limit t approaching infinity, negative e to the negative t, and then you have a plus e to the 0, which is 1. So if you look at it here, as t approaching infinity, e to a negative infinity is going to be 0. And so this thing is going to be just 0. And so this integral converges to 1. So again, as I said, and as expected, this one is an easy one. But because it was coupled with the next questions, which is this one, and I think this is the thing that started to get people wrong on this. So we put it limit t approaching infinity 1 to t n of x to the fifth over x dx. And again, you do a simple substitution. And this is what you have. And again, the boundary doesn't really change, except for the fact that you have x. And u going from 1 to infinity. So here you're going to have 0 to infinity. Limit t approaching infinity, 0 to t. U fifth du. So here you're going to have limit of t approaching infinity, u 6 over 6, 0 to t. So this one is where you have, if you plug in t approaching infinity, you have t to the 6 over minus 0. So this term as t approaching infinity is going to be infinity. So this one, this integral is diverges. So this is the one I think that got people wrong the most. So make sure that when you take integration or when you plug in, do not forgot any changes. They say if you do the u substitution here, make sure that you check for the boundaries as well. So that's that. If you be careful with these questions, then you should be good for this exam, this kind of question in the exam. Now, next question is suppose that every term of this series are positive and the series is convergent. So this series have every term positive and convergent. Which of the following series are also convergent? Now, for this one, I'm going to use the first one here is when you have the series, you only have an is convergent, series of an is convergent. But every term now is divided by 2 to the n. So I'm going to do a direct comparison test. We have 0, everything here, an, is positive. So if it divided by 2n, it's also positive. And this one is smaller than an. And then you have limit of n approaching infinity, an over 2 to the n. This one here, since you have an, the series of an is converges. So you have limit of n approaching infinity of an is also 0. That is one of the property of convergent series. Then you have here is a converge something 0 divided by a number by infinity. So it's going to be just 0. Then this thing by direct comparison test, you have this series an over 2 to the n is also convergent because it's smaller than a convergent series and that limit is also approaching 0 at n is going to infinity. This thing is also convergent by direct comparison test. So we have one series convergent. Now the next one is an plus 2. So here I'm going to split it into two series. So here you have this series is convergent. But then here you look at this one. You notice this term always have, so this kind of like the series of Bn where you have Bi is equal to 2. So all B equal to 2. So when you have limit of n approaching infinity of Bn, it's going to be limit of n approaching infinity of 2. So this is just 2. And so this is different than 0. So this right part is divergent. So this one diverges by test of divergent. And so because one of the complementary series is divergent, then you have the big series is also divergent. So the important part here is being able to notice this kind of series where you have every single term in the sequence be a constant. And so, so this one is divergent. And the last one in this exercise is that suppose every term of this one are positive again, is this one convergent? And so I think this one will better be clear if you were given one of the example, because there's not really any test that you can do with the root. Because you have given a root here and you don't have you have a root test, but you don't have something like a power test. So what I'm going to do is that I'm going to give you an example of a positive and convergent series. But that if I can show the fact that there's one series that say maybe make it divergent, then this this kind of like statement is wrong. Or you can, if you can show, so so you have, if you have an is 1 over n to the n, 1 over 2 to the n, or maybe even like 1 over 6 to the n. Clearly you can see every single term in this sequence is positive and the entire sequence is convergent by geometric series. So therefore when you take this one, the series of, then you're gonna have 1 6. And again, if you take limit of n approaching infinity of this Bn series, the Bn series, then you're gonna have s equal to 1 6 again. And based on the previous example, you can say this series or this one is divergent by test of divergence. So if there exists one of the series that makes this situation not convergent, then it means that this statement is wrong if you say it's convergent. So I think the hardest one in this part of the exercise in this third series, try to identify if it's convergent or divergent. And I think this one is works out if you try to make some, maybe like give it some example, because when you have like the root here, you don't have something like a power test to deal with it. So make sure that you have a note on that. So next one is also the last questions I have for this review. I don't think this is a hard one, but I saw 2 people got this one wrong. So I think I should go through it again and make sure that you understand it. So exam review, determine if the series is absolutely convergent, conditionally convergent, or divergent. Now again, you have an alternating series. So the first thing I'm going to do is that I'm going to find limit of, not limit. So if you can identify if 1 over n, ln of n, is convergent or not. If this one is convergent, then you can conclude that it's absolutely convergent because it's the absolute value of the series. But here, when I look at it, I think it's divergent. If you have a look back at one of the exercises that we did, I think in week 8, when we go over integral tests, this is one of the scenarios. So I give you one of the exercises, say 1 over n, ln of n to the p. So what value of p is going to give this series convergent? And that's when you have p smaller than -2. But here, p is equal to -1. So I would say in this case, I would expect it's a divergent series, but to make sure, I'm going to use the integral test again. So the integral test require that every single term in this series, so you have 1 over n, ln of n, is positive, starting from n bigger than or equal to 10. So you have every single term is positive, decreasing function, because you have, as n grow bigger and bigger, the denominator with n and ln of n. So it's going to be a bigger and bigger denominator, meaning the fraction 1 over n ln of n is decreasing. And then now you're going to look for, say, we can go back a little bit. I kind of forgot the conditions for the integral test. So the integral test condition is that it's bigger than 0, continuous, and decreasing on that. So now then you compute this integral to see if it converges or diverges, because it's kind of like related to the sum that we're looking for, the impartial sum of the series, but it's not directly. So now we're going to find the integral from 10 to infinity of 1 over n ln of n, maybe dn. Or you can just write at 10 to infinity 1 over x ln of x dx. It doesn't really matter with the name of the variable that you're using. So this one, if you put u equal to ln of x, du is dx over x, and you do the change of variable ln of 10 to infinity. So this one is from ln of 10 to infinity, u du. No, actually, it's 1, oh sorry, not there yet, 1 over u du. Or you can have limit of t approaching infinity, t ln of 10. And so this one is really easy. It's going to be just ln of u, with this one be infinity and ln of 10. So this one, clearly, when t approaching infinity of ln of t minus ln of 10. So this one clearly is divergent, and this one is just a number. So here, you're gonna have, this is the divergent series. So I said this one divergent by integral test. Now, because it's divergent. But this is just the absolute value. As I said, whenever you have an alternating series, you have to make sure you check it with the alternating series test as well. So I'm going to look at this one. And again, we just said that it's a decreasing term in the sequence. And so you just need to find limit of n approaching infinity, 1 over negative 1 over 1. So when you take limit of n approaching infinity, you take the absolute value of the n term in the sequence. And this one clearly is 0. Therefore, this one is convergent. So I will say this thing here, this series, 1 over n and 1 of n is divergent, but the original series converges by the alternating series test. Therefore, my conclusion here is that it's conditionally convergent. Somehow I look at this and I saw a lot of people think that this is absolutely convergent. Maybe it's because of here. You guys might have made some mistake with using ratio or root test. In this case, I don't even think that ratio and root tests are beneficial, because when I use ratio test for this, I got the ratio to be 1, and so it's inconclusive. So I would recommend maybe you use look at this answer that I have and see where you get it wrong, because most of the students try to avoid integral tests, but here the fastest way and the most sound way that you can use to solve this problem is using integral tests. Now, having said that, as you already see in the next slide, good luck with the exam, and I'll see you guys next week. Make sure to review a lot of the series and maybe like the improper integrals, because I found like a lot of people got that one wrong. Intermediate limit, not that many people get it wrong. So again, good luck on the exam, and I'll see you guys next week.